Hello, my name is Christopher Thrawn, Associate Professor of Mathematics at Texas A&M University, and I'm here to talk to you today about epidemiological modeling, an introductory presentation with demonstrations. A little bit about myself. I did my undergraduate degree at Princeton University. I did my graduate degree in mathematics at University of Wisconsin. After that, I went to China and taught at 3 universities in China as a foreign expert. When I came back, I worked at Motorola, which later became Freescale, working on semiconductors for the communications industry. I was a systems engineer. After that, I joined Texas A&M University, Central Texas, as assistant professor. Since 2013, I've been visiting Africa. I've visited Nigeria several times and given workshops and classes, as well as conducted joint research. And I've been visiting Sudan since 2017. Here's my family, my wife, and 4 children. We live in Texas, USA. And let me give you a presentation overview. In this presentation, we will answer the following questions. What is mathematical modeling? Why is mathematical modeling important in epidemiology? What are the limitations of epidemiological mathematical modeling? What does mathematical modeling have to do with data science? I will also explain the following concepts. A multi-compartment model, SIR is the basic multi-compartment model in epidemiology. I will talk about flattening the curve. If you've heard the news about COVID, they often talk about flattening the curve. So I'll explain what this means in terms of mathematical modeling. Herd immunity, and you will see how herd immunity works to control disease. Reproduction number is a very important concept in disease control, and endemic equilibrium and disease-free equilibrium are also important concepts. So this is my overview. First of all, I would like to explain what I mean by modeling in this presentation. There's really 2 types of modeling in epidemiology that can be called mathematical. There's mathematical modeling and there's statistical modeling. And they are closely related, but also different. Mathematical modeling attempts to analyze the dynamics of the spreading of contagious diseases in populations. So it tries to understand the mechanisms or how things work together to cause diseases to spread or to become extinguished. Statistical modeling attempts to describe the behavior of diseases that spread within populations. So statistical modeling describes, mathematical modeling analyzes and explains. You may have had some exposure to statistical modeling. Tools for statistical modeling include regression, time series, data mining, and so on. So statistical modeling is taking data and trying to fit models to it, and the models do not relate to the underlying dynamics. You can understand this in terms of physics. Physics is a dynamical theory. It has equations that reflect forces, accelerations, and so on, which are causing motion. That's a mathematical model. A statistical model would simply be take the data and try to fit it. Statistical modeling is generally used for short-term forecasting, while mathematical modeling is used for long-term and what-if scenarios. What is a what-if scenario? It means, suppose I do something, how will that change the behavior? So mathematical modeling can do that. You can change some parameter in the mathematical model and see how that changes the future. With statistical modeling, you are only fitting data and it's just a description. So in this presentation, I will talk about mathematical modeling. Why is mathematical modeling important? Use mathematical modeling to understand the important factors that affect the spreading of infectious disease. You can also use mathematical modeling to make predictions of future disease levels. When you see predictions on the internet or curves that show what COVID will do, these are based on mathematical models. Mathematical modeling is important to evaluate the effectiveness of policies to control disease. Here I am talking again about what-if scenarios. Suppose we do more distancing. How will that affect the course of the disease? Suppose we start testing. How will that affect the course of the disease? Mathematical modeling can be used to make predictions about these things. In the current COVID crisis, policymakers must make costly choices, whether to shut down businesses or whether to open up businesses. Shutting down businesses costs jobs and money. There's an economic cost. Opening up businesses may cost lives. So mathematical models can inform policymakers of the costs and the risks of choices. So mathematical modeling is a very key tool right now in the control of COVID virus disease. What are the limitations of mathematical modeling? Epidemiological mathematical models have limited accuracy. Now, why is this? Because these models require parameters. How infective is the disease? How mobile are people? How long does the disease last? These are all parameters. Parameters are not completely accurate. So these are things that I should know, but I don't know exactly. So I can call these known unknowns. Now we also have model error. The model that I'm using and the equations that I use to describe the disease may not be correct. There may be some approximations involved, or there may be some factors that I don't even know about. These I would call unknown unknowns. So just remember, epidemiological mathematical models have limited accuracy. Mathematical models should not be taken too seriously. They cannot give exact predictions. However, they can be used for worst case scenarios. What does this mean? This means, how should I prepare to be prepared for the very worst thing that can happen? You don't want to over-prepare and spend too much money, but you don't want to under-prepare and have the epidemic go out of control. You want to find a reasonable set of measures to take in order to control the disease. Now, in the United States, it was known that COVID would come from China, and they took some measures to close off flights and limit transportation. However, these measures were not enough, and as a result, there are over 8 million cases of COVID in the United States. This is because of inaccurate parameters and unknown unknowns. These things were not known, so those who modeled the spread of the disease did not anticipate the virulence of the disease. And as a result, as I said, 8 million people and tens of thousands of deaths have occurred. So in that case, unfortunately, the worst case scenario was not properly evaluated, again, because of these issues. Mathematical models can also be used for sensitivity analysis. This means, suppose I change the level of treatment or the level of distancing, how is that going to change the result of the disease? So sensitivity analysis says, if I make some adjustment, how is that going to change the course of the disease? I can also use mathematical models to make a qualitative comparison between the treatment's effectiveness and cost. You can compare one treatment versus another treatment. And mathematical modeling can give you some idea of which treatment is more effective in terms of cost. Okay. What does mathematical modeling have to do with data science? Data produces better models. Data can be used to estimate model parameters. For example, we will see later that one of the parameters needed in the mathematical model is the number of contacts between susceptible individuals who do not have the disease and infected individuals who do have the disease. If we have some data, we can estimate the number of contacts. So data is needed to supply these parameters. More detailed data enables the use of more detailed parameters. If I have data with more details, then I can include more parameters in my model and the model will be more accurate. More detailed data leads to better parameter values. More data and machine learning may be used to construct better mathematical models. In modern machine learning, the machine learning is used to actually construct the mathematical models because these machine learning algorithms are becoming more and more sophisticated and more like people thinking. So data produces better models. Models can also produce better data. The model will tell you which data is important and it will tell you what data to collect. The model can also be used to help select data features used in data analysis and machine learning. So models tell you how to look at your data. Okay, so I will stop here and we'll pick up with the next video.